Alright, silly people, here's the situation. Uh, Griffiths is going to have us construct every matrix that ever existed um, in like three different ways. So to represent any matrix that could ever exist, the letter is going to be T. Um, and the first way we can construct it is by adding together a symmetric matrix plus an anti-symmetric matrix. Um, we just have to figure out what those two matrices have to be in relation to T uh, to know how to do it. And to do it, you can use a couple of different facts. That the S, by definition, it's a symmetric matrix, so it is equal to its transpose. And then A, by definition, being an antisymmetric matrix, will be equal to minus its own transpose. So what I did was I took this equation and I solved it for S. So I had S is equal to T minus A. And I took the transpose of the equation. So we have S tilde equals T tilde minus A tilde. And then I set these two expressions equal to each other because they should be equal to each other. And so we have T minus A equals T tilde minus A tilde. Minus A tilde we know is just equal to A, so we have that T minus A equals T tilde plus A. Solve that for A, and you get that T minus T tilde over 2 equals A, right? And then you can plug this back into this expression for S, and you get that S equals T minus T tilde over 2, right? And then you can just carry that algebra out, and you'll find that it is T plus T tilde over 2, which makes it out in the end. So we know what S and A have to be in terms of T now to construct it this way. And if you want, you can put it all back together and say that just T is equal to S plus A. So it's T plus T tilde over 2 plus T minus T tilde over 2. The T tildes will cancel out. So you have 2 times T over 2, which is T again. So, facts. You can definitely write any matrix as a sum of a symmetric matrix and anti-symmetric matrix given by these two forms. These algebra steps will be identical for the next two scenarios that will follow. So the next one that Griffiths wants us to check is, can you construct every matrix that could ever existed by adding together a real matrix plus an imaginary matrix? The facts are that any real matrix is equal to its complex conjugate, and that any imaginary matrix is equal to minus its complex conjugate. So you just solve this equation for R, you get that R equals T minus M. Then you take the complex conjugate of this equation, you get R star equals T star minus M star. You set the two expressions equal to each other. T minus M equals T star minus M star. Use the definition of minus M star, so you get T minus M equals T star plus M. Solve for M, you get M equals T minus T star over 2. Plug this back into this equation for R up here. You get R equals T minus T star over 2, which just gives you T plus T star over 2 for R. Awesome. Finally, he says, well, what if you wanted to construct it um, by adding together a bunch of Hermitian matrices, so T equals H, plus a bunch of, then the rule for Hermitian matrices is that they are equal to their own Hermitian conjugate, and also that the skew Hermitian matrices are equal to minus their Hermitian conjugate, right? So we actually just have uh, H equals T minus K, just solving this for H. Take the Hermitian conjugate of this, you get H dagger equals T dagger minus K dagger, and then solve or equate these two expressions. So T minus K equals T dagger minus K dagger. Use the definition of minus K dagger is just equal to K, so T minus K equals T dagger plus K. Same thing, you just solve for K, you get T minus T dagger over 2 equals K. Plug this into the expression for H up here, and then you get that H equals T minus T dagger over 2, which means it's T plus T dagger over 2. Crazy stuff.